Awesome. Hi guys, my name is Linda, and my talk today will be about total smart contracts in Pact. So to start off, I just kind of want to break down what the talk is going to be about. We are going to do a quick introduction of what Kadena is, who I am. Then we're going to talk a little bit about Pact and some of the decisions that we made for why we made it the way we made it. And then I'm going to talk about some Pact 3.0 features that we are very excited about because we think that it improves security and safety. Okay, so I'm going to start. So what is Kadena? So Kadena and the company I work for is a hybrid blockchain company. We have a public blockchain that uses proof of work. It's currently in V1, and then mainnet is coming in October. And then we also have a private blockchain called Scalable BFT. And we also created our own smart contract programming language using Haskell. So actually, all of these softwares were created using Haskell. And so in our smart contract language is called Pact, and it can be used both in Scalable BFT and in the public blockchain. So who am I? I'm a Haskell software engineer. I graduated with a computer science degree from Columbia. I've been at Kadena for a year now. And while here, I've been part of a couple of features. One of them is called Pacts, which are like multi-step transactions. So let's say you start a transaction. You want to start an action in one transaction and then continue it in another one. So I was in charge of figuring out that logic. And then I was also part of the team that got Scalable BFT on AWS. And then finally, one of my most recent ones is allowing support for ECDSA cryptographic signatures on Pact. So right now we support ED 255.9. So I added support for that one, and also in the future we could add more cryptographic signature schemes. So why Pact? So Pact was specifically designed to be safe by design, and is supposed to be fast interpreted, and is supposed to be legible, not just for like your programmer, but also for your business user. The business user is not intended to be able to write Pact, but they should be able to understand it. And it's open source, and it was built with Haskell. So a big question that we get asked is like, why didn't we use a mainstream language? Why do we want to create our own programming language for smart contracts? One of the main reasons for that is because a lot of mainstream programming language are non-deterministic. And so in blockchain, if you're familiar with blockchains, every transaction that you do comes at a cost. So you have gas associated with it. So why would you want to allow for transactions that could potentially go on forever? So that just doesn't make sense with the use case. And then moreover, there are certain features that mainstream languages allow that we thought would not be safe enough for a blockchain language, such as null pointers or unsafe type conversion. And then the Turing-incompleteness aspect of a lot of mainstream programming languages is related to its non-determinism, and in a lot of ways has been the behind some of the bugs that we have seen in like programming languages like Solidity. And so this is one example. It's called the Rubik seed bug, and the kind of title for this is like mainstream paradigm strikes, because this is a smart contract, and the contract got renamed, but the constructor did not. And so anyone could become the owner of the contract. And so in mainstream languages, if you were just writing this up in your day-to-day job, this would be a quick fix. But in blockchain, it becomes very expensive because you have to update it. And in Ethereum right now, you can't update it. And so this becomes a very expensive mistake. Right. So because of all these reasons, we've decided to create a smart contract language that is total, that is deterministic, that is blockchain specific. And we took the approach of being a little paternalistic. And so what I mean by this is that we are not going to allow certain features that could result in a program not terminating, such as recursions or infinite list. But also, we wanted to create a language that made use of blockchain-specific criteria. And what I mean by this is, an example, we have a key set data type, and so in blockchain, you make use of public-private keys, and so having a language that has this notion of authorization built in is very important. And also, because blockchain is at its core a database, we wanted a language that was friendly to database. And a lot of the syntax, as you might see, is very SQLite-like. So assuming that, so from this slide, the point was that we created a language that is hard for you to kind of shoot yourself in your own foot, or whatever the idiom is. But at the end of the day, software engineering comes with bugs, and you're going to write bugs. That's just part of the game. So we wanted to create some tools to make it easier for you to catch these bugs before you deploy them to the blockchain. And so some of these features is type checking. So we have opt-in type checking. So if the user wants to type check a function or a schema for a database, they can do it, and it would be checked at runtime. So if you type check your schema and you're doing an insert, you will be type checked every time you interact with the database. So another thing that we give, and I think it's maybe most of the reason why you guys are here, is we have formal verification. So we allowed programmers to specify properties that their functions must satisfy. And so we think that this is a really powerful tool. And towards the end of this, I'm going to show you guys an example of this. And then lastly, we have something called REPL testing, so Pact. You can simulate a blockchain transaction locally using REPL. So you can simulate the beginning of a transaction, the committing a transaction, and so forth. So this allows you to quickly check that your function, for instance, doesn't have any bugs, or just do some rapid unit testing. And again, I'll show an example of this in action. And so another feature that we thought was very important, and that we think is a detriment to the current state of affairs with Solidity, is that at the end of the day, it gets compiled down to bytecode, and that's put on the blockchain. But it's really hard to rationalize about what, I don't know about you, but I can't read bytecode. And so we made the decision that code is going to go on the blockchain. So if you are interested in knowing what the source code of a contract that you want to participate in, what that is, you can look it up and then you can read it. Not only you, but like I mentioned before, a business person could read it and potentially understand it. So we think that there's a lot of benefits to this. Most of all, transparency, and trust with the user that the code that is on the blockchain, that is what is going to be executed. So that's one of the things. And then lastly, let's say that after all of that, a bug still went through, because that happens. What do you do then? In Ethereum right now, it's hard to it's impossible to upgrade, I think, your smart contract. But with Pact, we have this sense that code has an ownership. And this concept of ownership of code, of governance of code, is expanded a little bit in Pact 3.0, which I'll get to. But at its core, it means that you can upgrade your code, not only to fix a bug that you saw, as we have seen a lot of bugs in Solidity smart contracts. You could deploy a fix, but they don't allow it right now. Or you could include new features if that's what you wanted to. So that's kind of, so to recap, that's kind of what the reason why we went with Pact specifically, and why we chose to make it human readable and have it be upgradable and be blockchain specific. So that's kind of that aspect of it. And so now I kind of want to talk about some of the new things that have been added to Pact 3.0 that expands upon these themes that I just touched upon and goes further. So the focus of Pact 3.0 has been about authorization schemes and like being able, as a programmer, for you to program authorization schemes. So what does that mean? So one of the new things that was added was called GARs. And so GARs are predicate functions that can pass or fail. So Pact has always had the feature that you can enforce that a certain key set is in the environment. So like, let's say that you want to make sure that only the user for this, let's say you have an accounts table and you have an amount associated with the user, and then that user has a key set that you have stored. You want to make sure that any transfers of that account is only done if the user of that account authorized it. So Pact has always had this sense of authorization and enforcement of key sets. But now we've expanded it so that you can write predicate functions for any scenario in which you can think of. And so, any scenario that you can write in Pact. So there's key set enforcement, there's module enforcement. So like, let's say that you want to make sure that there's a function in your module that only the owners of the module of the smart contract should be able to do. For instance, kicking someone out of a club or something. Guards allow you to do that. And so this is just one example of what guards let you do. And so the next concept that I want to talk about is, okay, so now you have this function that can pass or fail depending on like certain criteria as being met. How can you control what code executes because of that permission? And so with this, we introduce this concept of capabilities. And that's kind of like what the syntax looks like. When you can define a capability. So like, what are capabilities? And so capabilities in Pact have a history associated with it from like the traditional computer science literature. So you have capability-based security in which resources and system functions are tied to certain tokens or certain permissions. So we've kind of narrowed this down a little bit more to say that certain code can only be executed if certain rights are granted to you, and that right is granted at that level. And so capability not only has a history in CS, but also has a history in blockchain in general. So with Bitcoin and Ethereum, you have tokens that are associated with your account, and so therefore that resource is tied to your token. And so with capabilities, we kind of took this notion that's already there and applied it to Pact to make it so that the programmer has more control over exactly what code gets executed given certain conditions or given certain rights. And then we can expand this further now that we have this notion of capabilities, right? We can apply it to smart contract ownership, aka governance. And so what this means is that the programmer can, whatever governance scheme they can think of that can be written in Pact, obviously, they can make it that's what governs who can upgrade or change a smart contract. So again, Pact has always had key sets, so modules have often been associated with key sets. So usually like the admin could upgrade or change a module. But now you can also have things such as decentralization. So let's say that you want to make sure that your module, or sorry, I say module, but it's kind of equivalent to smart contract. So like your smart contract, let's say that you want to make it so that your users have to vote on the hash, on the new hash of your smart contract. You can program that. And there's an example of that if we have some time at the end that I can go through. And so one last thing we have is formally verified interfaces. So this is actually a feature that Emily in the back was very important, was the creator of. So our interfaces in Pact are like type classes in Haskell. So you can say, if you implement this interface, you have to have this function with this return type and inputs and so forth. But we've expanded it more so that you can also put module constraints. You can say the return type of this function must always be divisible by 2 or something like that. You can obviously create more like juicier properties, and I'll show that right now, actually. So I'll switch over to going through some Pact code. First of all, any questions? Yeah?
Are those model constraints similar to like type class laws that you might want to enforce?
Yeah.
Instead of low-hanging abstract laws like divisible by 2, you can actually write more complex laws like how the inputs and the outputs interact with each other in terms of their type, or even if the future holds how to interact with the table, for a different table type. Yes, like type class laws. Except you also have, because we're running a Z3 for our home verification reason, you also get some common inspection as well.
Yeah, so this first example is kind of to highlight governance and some of the cool things you can do with it. So this is a simple, so this is the REPL, what I was telling you about, and Pact in Atom has linting associated with it. So it tells you kind of like what's returned from that. So in that one, it's like loaded the module. So if an error occurs, you'll see like a little red dot. So keep a lookout for that. So in this module, we're just specifying a scheme for an account, right? It's very simple. And then we have a function here. We have this here that says that the owner of this account module is going to be governed by account governance rules. And account governance is a capability that you define in the module itself. And so this is a very simple one where we just say, okay, the owner of this is whoever has admin rights. And so we call this function, and this function is a guard that is reading a key set from the environment, and that key set, it expects it to be named admin key set. So this key set is defined here. You can specify key sets in different ways in Pact. You can say, actually, let me go back a little bit. So Pact has always allowed for multi-signatures. So you can always say, you can always sign things with multiple signatures. So you can be, Emily is the owner of this, but so am I. And then more than that, you can say, in order to do anything with this key set, both Emily and I have to sign, or you can specify only Emily has to sign, or only I have to sign. So in this case, the default is everyone that's specified has to sign, and the syntax varies, and you can say any of them need to be there, but I can show you the reference docs for that later. But in this is just saying, this module called account module is owned by the product department and the dev department. Any change to this module needs to be signed by both. So that's all it's saying. But let's see it in action, right? This is what I was telling you about, like simulating the blockchain. So we just committed this in the REPL, and now we're starting a new transaction, and we're saying, hey, I want to upgrade that account module that I just loaded, and I'm going to add a new column called like active, like if your user is active or not. And so the reason why you don't see any errors here is because the environment keys have both of the keys from the admin. But let's say, for some reason, I was mistaken and just signed it with like the dev department. Then you have a key set failure saying keys all. And what that means is that it expected both the dev department and the product department to sign it. And also fails if you give it no keys. So that's just like a straightforward example. Any questions right now? Yeah?
So those blue dot, or the N keys and the NTX, those are things that are part of the REPL languages, but not part of Pact, the contract language. Is that correct?
So there are certain REPL-only functions, such as begin transaction, right? But what's returned from when you load a module is going to be this as well, like loaded module account, whatever.
Okay.
Yeah.
Of what's going on. So think of those as like the top level signals.
Yeah. So as we saw the key set, admin keys and enforcement in play. But let's do something a little more interesting with governance. So now I want to upload a module called Hello Coin that just does like a simple transfer and makes use of this accounts schema that we specified in a previous module. So in here, we're doing something a little tricky. So here, when we do use account module, we're loading into scope that module the account module. And what that means is that we have access to its functions. And one of those functions that we wrote was this function called enforce account admin. And so enforce account admin enforces that the admin key set is present in the environment. And when we use it as the governance capability, that means that to update Hello Coin, you need to have the same privileges as to update account module, if that makes sense. So both the dev department and the product department must sign in order to change it.
So on chain with various contracts to trade, could you use modules from other contracts, or it's just all the same?
Yeah?
You can import.
Yeah.
You can import modules so long as you have key sets to actually access them. Yeah. So there's sort of like a global namespace
Yeah.
of all modules that get published across the entire thing.
Gotcha.
And you can import whatever you want, so provided you can actually use it.
Yeah.
Dynamic linking in a sense.
No. Do you want to mention?
Namespaces?
It's actually inline.
Okay.
And that's so that upstream people cannot break or contract. They can't like how we usually have in a language where a library change upstream could like blow out like your contract. So that these contracts are perfectly reproducible. Anytime you have a basically an import or like a require statement like that, they can launch it all.
The whole thing.
The whole thing.
Yeah. So you can use functions from other modules as long as you can use it. So like if someone says like enforce that the admin can only use this function, then you won't be able to do it unless you're the admin. Right.
If you just wanted it publicly available, you would just not enforce any key set.
Yeah. Yeah.
Does that mean that if you said that you don't want upstream changes to break your contract until you inline it, but presumably then upstream changes can break the compile process of your contract if those changes isn't happening? It's like the inline might no longer work.
This is an important point. A module that has been upgraded is distinct from a module that hasn't been triggered, and you distinguish them by hash. So when you have code that imports one version of a module, you're importing a specific hash of the module, and all its code, and the distinguishing of the hashes is the thing that separates any changes in workload from the same value.
Yeah, so remember when you asked what the little blue dot was? When you load a module, you get the hash of that module. So if you see this hash starts with like 02, and then when we upgraded, it starts with like HV, just because it changed. Right, so we've talked a little bit about HelloCoin. So again, if we want to upgrade it, we have to realize that both product and dev departments must sign. And then, again, very simple example, let's say only the dev department signs it, then we see an error. Because HelloCoin requires the permissions from admin. Yes?
So then, when you're making a call on line 90 to use account module, to which version of account module? Is there any way in line there to distinguish between versions? Because internally it refers to hashes.
You can bless a module, right?
There's you can pass the hash instead of using the name, or you can state which version, using a keyword which has been mentioned here called bless. You can bless hashes of modules that are successive with previous versions that you are going to allow that type check, basically. So in a sense, you get a distinct contract, which is the same contract, and you just differentiate by version.
But what you're saying is that if two versions of this contract are morally equivalent for your use, that you can bless both of them, and because there are no observable differences, they're the same.
Cool. So that was the example for kind of governance. And there's if you go to Pact, read the docs, and you can just Google that, you'll find a more interesting example on how you can describe like a decentralized governance function. If we have time at the end, I can go through it. And so in the second example, I kind of want to talk a little bit more about capabilities and kind of see them in action. So in this example, we're still using that account module from the previous one and the HelloCoin from the previous one. They're just a little more simplified. But actually, let me quickly show you. So part of the update that we did to HelloCoin was to add this enforce, this enforce statement that is essentially checking for whether the account that you want to take money out of has enough amounts to do that, because we never want to get into a state where we have a negative balance. So this is something that Pact, like a feature of Pact, where you can essentially throw an error and say this is not valid, exit. And so with governance, now we can essentially take that enforce statement and put it into its own capability. Sorry, I said governance, but I meant capability. So this is an example of a named capability, which we are calling can transfer. So this is just saying what needs to be satisfied in order for you to transfer money. And so one of the things we're saying is, you have sufficient funds. So it's a very trivial example. But it gets more interesting when you get down to here, where you have this sense that you can, you have the scoped invocation of a capability. So with capability, as you see here, and I don't know if, with capability controls this part of the code. So, so with capability saying, hey, check this capability can transfer, are all of these rules satisfied? And if so, keep that permission in scope for this body of code. So this could be useful for a lot of reasons. Like maybe you want to, in the future, create a capability just for debit, right? So only people who have the rights to debit can even read from that debit account. Yeah, it's essentially so you don't bleed out permissions to other parts of the code that are not needed. So that's it for capabilities. Any questions? Yeah.
Is enforce like a string or a guard?
Sorry?
How does enforce, so we talked about guards earlier, but how does
Right.
enforce interact? Is it like a guard, like if it's not true, the computation is not possible?
Yeah.
Okay.
Yeah, so I think, let me, so they go hand in hand. Let me show you here. So they use kind of similar syntax where you can do enforce. But yeah, it's essentially, they're very similar.
Whereas I think the main difference is that it enforces takes the main statement, and then we'll just fail the whole thing. And your guess gets that way.
But yeah, with guards, the real like power comes from the fact that you can stipulate only the owner of this module can touch these tables or do this function, or even later on when you get to multi-step transactions called Pacts, you can say only this function can only be called from the Pact that like invocated it. So in that way, guards are a little more powerful than like enforce statements. So I guess we can move on to, I guess, the juicier example, which is formally verified interfaces. And in here, we're going to be pulling in what we've covered about capabilities. So this is, again, the same account module that we've been seeing. It just defines a schema. And then this is new. So this is the syntax for declaring an interface. So in here, we can declare an abstract interface in the sense that we can say, we can import like module. So if you notice, account module makes use of like schema. So like you could make use, you can say like, this function takes an object of this schema or so and so. In here, we're using it a little bit differently, but that's just like one example. So we're saying that anyone who implements this coin interface must have a function that returns a string that takes 3 arguments, the first of which is a string, the second is a string, and the third is an integer. And it's essentially like from to who are we going to debit, who are we going to credit, and how much. And so this is the syntax for specifying module properties. So in this first one, what we're really saying is we're going to look at a table called accounts, and we're going to assume that in that table you have a column labeled KS that is like a key set. So what this is saying is that that when we interact with the from user, like with the debit user, that the key set associated with that user is being enforced, is being in the environment. So you don't want to just take money from someone and they not know about it. That's what this is this is what this is saying. And then the second property is we want to make sure that amount is non-negative, just because then we will be taking money from the debit, but really we'll be adding and so forth. And then the third one is we want to conserve mass. So we want to make sure that no money is created or destroyed, kind of. So we want to make sure that the difference in account balance that we change is 0. So that so what that means is that if you took $5 from this account, you deposited this $5 to another account. And so then this is hello coin, and we are implementing this interface. And then here, this is a little different from the previous can transfer capability we saw. We're adding a couple other enforce statements. We're saying this enforce statement says that only the owner can do a transfer. And then we're also checking that the amount is 0, and so forth. But let's see what happens when I know that this is what will make it work just because I've tested it. But let's say that you're not really sure, but you just know that you have these properties to contest with, and you just start writing. Let's say that you just delete all of these. You're going to get some warnings. Where are the warnings? There's a warning right here. Actually, let's just do one at a time. So let's say that we haven't been enforcing this right here, that the owner key set needs to be in the environment. We see here that this is failing because it found possibilities of it found inputs that could violate the property.
It's important to note with this too that it's not just finding this stuff on the fly, but it's finding it in a lightning fast way, which is like microseconds and milliseconds. And you can't get this from any other sort of form of replication, which often takes minutes to verify easy with just like one plus one. And because we're using Haskell's FFI into Z3 here, we can actually just find these as you type, as opposed to after running something, waiting a bit and then finding out that you're going to solve.
Is it doing like example generation, or is it actually doing like actual algebraic reductions?
Both.
We actually, the way it's written in the back end is we actually build a predicate of symbolic expression from these models, and then we execute the tree, and if it happens to go through the property checker or it happens to go through the symbolic checker, then it would use one or the other. In this case, and it should use the symbolic checker.
Right. So now we know that this is needed, so we uncomment it. But let's go to the other one, and you'll see something similar. That then the second property is being violated. And then this next one is interesting because the reason why it fails. So these two, right? The enforce statements, you can kind of see that they're kind of similar to the property, in a way. You enforce that an amount is non-negative and so forth. But this one of like enforce this, I think really highlights the why the property checker is really useful when you're programming, because I think it gave you an edge case here. So let's see. So let's inspect this a little more. So this, I don't know if you could see, but like the from and the to, the reason why this is invalidating is because it's saying that the from and the to are the same. It's just quotation marks because it's a string and it just randomly generates a string. But it's because it's the same. And if obviously mass conservation, you think you can rationalize that it's important, but I didn't necessarily think that the edge case that would make this fail in this case would be because the two and the from are the same. So it's just an example of like how when you specify certain properties, it can actually help you write better code.
Yes, what you're saying is that you didn't have to be force wasn't identical to the property.
Yeah.
Like you didn't have to explicitly check for the conservation of mass, that because like sort of the property like sort of failed in an interesting way.
Yeah.
You check for the way it failed.
Yeah. So like let's say that there was another case in which it could fail, like the mass conservation could fail, and let's say the example it gave us, we could say, oh, it's because the to and the from are the same one. We write it, right? But let's say it keeps failing, then you can look at the next example that it might show you to try to understand why.
And then either write another or sort of generalize.
Right, or write better code or probably another enforce. So that's the examples for right now. There are a couple others. I think we have like 10 minutes. There are a couple of things that I could show you. I could go through read the docs, and we can go through some of the other property checkers, like some of the other properties that we support. And we can also look at an example of like decentralized governance, but also if you guys have questions. Yes.
Is it publicly accessible?
In Pact? Yeah. Pact is open source. I think you can just do like npm, like if you're a Mac, like npm, like in brew, just brew. Yeah. And Pact 3.0, I think it's on brew right now. Or if you have Stack, you can go to the source. Oh, it's on GitHub. Yeah, so you can just. This is the code right here, and obviously, more than welcome to play around with it, break it, and let us know.
Or even if you feel like it is 100% hackable, that's like 32. So, you know, anyone wants
I think you had a question. Yeah.
Yeah. Does the formal verification just run on the developer's side when they're using the REPL, or is it something that blocks that accept the code into a new block, or nodes that verify a block? When they accept the code into a new block, do they run formal verification and reject the block if it doesn't check out?
That's a very good question. I believe that it's you have to do it in the REPL. So right here you see this verify hello. That's what's triggering it. So let's say I comment that out and I uncomment like this that we knew had thrown error before. You can see right here there's no warnings, but also if we go up, there's no warnings. So yeah, it's something that you have to opt in. So like formal verification doesn't mean that you're going to write perfect code or that it's going to solve all your bug problems for you, but it just means that it's a tool that you have at your disposal. That when you're writing software, you kind of have to try to test as much as you can. I think that's it. Thank you.